For this video, I wanted to go over one or two examples of centripetal acceleration and centripetal forces. So this problem, I love space. So we have a rotating cylinder in space that's like 10 miles long and 5 miles in diameter. So I'm just going to draw it like this. I don't know if my proportions are good, but there's my cylinder where this is 10 miles and the diameter here is going to be 5 miles. Now, of course, when we do a problem like this in physics, we want to put it into meters instead of miles. And so let's just round here. Let's say that this is approximately 16,000 meters in length. And then we don't care about diameters. We really only care about the radius. So the radius is going to be a quarter of the length, or about 4,000 meters. Okay, so this question has a lot going on. If you don't know where to start, I always start with drawing a free body diagram and thinking about the forces. This question is asking, this cylinder is going to rotate and create artificial gravity. All right, so we have this rotating cylinder, artificial gravity, and we're looking for the angular speed that the cylinder has to have so that the centripetal acceleration at its surface equals the free fall acceleration on Earth. So that sentence, to me, the first thing I think is I want my centripetal acceleration to be equal to the gravitational field strength, G. Okay. Now, this idea, you would have like people that would live on the surface. So, you know, they could be like cooking their dinners or sitting at their desks. All right. The forces that this guy feels as this cylinder rotates in a circle, there's not gravity because it's out in space. So the only force that this person will feel will be a normal force pointed towards the center of the cylinder. Friction if he's like walking around, but if he's stationary, just really a normal force that he's feeling. Okay, so I can start thinking, okay, well, my centripetal force is really the sum of all of my radial forces, which in this case is just my normal force. I know then that my normal force, or my centripetal force, equals mass times the centripetal acceleration. Now, this question, do I need to know all of that about forces? Not particularly, because this is saying the acceleration, the centripetal acceleration is going to be G. And so instead of thinking about forces, which is important, I can just look at the centripetal acceleration. I know that the centripetal acceleration is my tangential velocity squared over the radius. That equals AC. Now, this is all well and good, but in this problem, it asks what the angular speed must be, not the tangential speed. We don't care about how fast it's moving out here. We care about how fast the whole drum, how fast that whole cylinder is going to rotate. So we don't really care the speed along any part of the radii. Okay, so in order to do that, we need our bridging equation from linear speed or tangential speed to angular velocity, which our tangential velocity is going to be the radius times the angular velocity. If I plug that in to this equation here, I get omega squared times r is my centripetal acceleration or my gravitational field strength, G. That's what we said it was going to be, right? We want that inward force that this person feels to be the gravitational field strength. All right, so now we just need to solve for the angular velocity. So our angular velocity in this case will just be G over r square root. We can do the math on this, right? We can take then 10 meters per second squared divided by, we said, a radius of 4,000 meters. And then we'll take the square root of that. That gives us an angular speed of 0.05 radians per second after we do the square root. Okay, how fast is that? So the good question might be in what time does it take what's the time that it takes for this big drum cylinder to go once around? So 2 pi radians is our distance. So if velocity equals distance over time, then time is the distance divided by the velocity. So we take our 2 pi radians, divide it by 0.05 radians per second, and then we'll end up with the amount of time in for 1 revolution. That's about 125 seconds, which is about 2 minutes. That's pretty fast to think that this 5-mile diameter object space station could make a full revolution in 2 minutes. This is one of the things that you think like maybe you would not actually want a full strength of gravity in a space station. That seems like a very fast rotation.